Okay, so this is heat system design, week 3. We're still in chapter 2, which is energy and what does it mean to us. And if you notice, they spend the whole chapter trying to define energy because these little ideas will carry through with you as we talk about insulation, about losses, about material selection. So knowing the basics is going to help us understand what are we working with. So we said energy and power are different. Energy is a quantity of stuff. Power is how we spend it. The dry cell battery has energy in it. And how fast we spend this energy is the power. How much power we take out of that battery. We can make it last for 2 days, or we can spend it right away. Same with gasoline. So power is a rate. It's a function of time, heat, and work. So heat is energy. Work is work. We did something, we moved something, there's displacement. If the car is idle, is it doing work? No, but it's consuming energy. So energy is a quantity of amount of work we can do, and heat is energy, but does it do work? Not all the time. Work is when you actually do displacement. So what does that mean? That means, again, if the car is idling, we are consuming energy, but there is no work. So work is a function of how things that move from one place to another has to do with distance. So they're different things. Pressure versus flow. So if we, from the last class we were saying, if pressure is voltage, what is flow? Current. We're going to use the same analogy with heat. So if we have heat as our energy, and the amount of heat is pressure, the flow of heat can be like current. So thinking about that, if this is a wall, the inside is 60 degrees Fahrenheit, and the outside is 90. So if we think of heat as energy and as pressure, which direction do you think the heat will move from? This is outside.
Outside to inside?
Yeah, it's going to move this way. This is going to be my flow. And would this be my resistance? Okay? So, it's going to be my flow. Do you think the flow will be affected by how hot it is outside?
Yes.
Yes. If it's 60 in here, will there be any flow?
Not really.
No. There will be no flow. If we are at 50, what will happen to the flow? It will reverse.
Opposite, yeah.
It's going to go from naturally from hot to cold. So let's stay with the first concept, which is, let's say it's 90 outside. So we agreed that the flow does change by the amount of heat. And if I fill this wall with insulation, this will slow down. Be less flow. There's always going to be some flow, but we're going to slow it down faster. So that's pressure. If pressure is the amount of heat, it's related to the flow. This flow is related to the material, the temperature, and also the area. What if the wall is smaller? Is it going to be less or more flow?
Less.
Less flow. Big wall,
More.
big flow. Big window, big flow. Small window, less flow. So based on that, I can say the flow of heat does flow. The area, exposed surface, and what else? We said the material,
Yep.
material. And what else? Temperature difference. We agree? The flow of heat is a function of the area, how big the wall is, what is the material of the wall, and what is the temperature difference. Those three things what we are going to use to manipulate heat flows. Put insulation, reduce the area, reduce temperature. Question?
What's it as word?
Temperature difference. Sorry. It's too high. Okay, so and now we'll talk about types of heat flow. How does heat flow through material? Little by little we'll get the concept ready. But now we agree on this. So if I want to make things less wordy, I can just give them symbol. Can we do that? Just so we don't try too much. I'm going to call this Q. Well, not me, but it doesn't. And this is area. And this is U. And this is delta T, temperature difference.
That's the equation.
Yeah. So, when you go and buy insulation, this is insulation you can put in the walls. Usually they sell you, some of them have the number. R4, that means the resistance is 4, and that's gonna go in here.
So our unit for this equation would be time per unit area, or?
Yeah. Yeah.
So,
Any question? Complicated?
A little bit.
so the only thing governing the flow of heat is the temperature difference.
And the material.
Well, that's gonna be constant.
Yeah,
The
true.
area and-
But you can change it as well.
Yeah,
Yeah, you can add stuff to it.
yeah.
Or the area there is gonna be constant, because otherwise you have to close the wall or something, but they're gonna be in some area. So temperature difference is always going to change, and you have no control over that. It's the weather. You can control what you want inside. You can go from 60 to 80. That's what you can control. Material, that's something we can control. You can add insulation, add more layers, have, and instead of R4, they put them together, it's gonna be what, 8? Yeah. And I will show, we can add some more, we can get something thinner with more R value, resistance. And I'll show at some point how there's a function that adding insulation to infinity is not gonna help. There's a point when adding insulation is not gonna help. So you cannot just keep adding insulation to infinity. So we'll talk about that later. Okay, so energy is quantity, power is energy per time, piece of coal, plus fuel, amount of energy and how fast we spend it. Think of gallon of fuel oil, car horsepower, and torque. Horsepower and torque are all power of the car based on the engine design and how much it consumes fuel. So if you think about torque, usually trucks have high torque. Also, they have bigger cylinder heads. Bigger cylinder size, so you have more force per area. I'm not going to go into the mechanics of it, although I'd love to, but it's not complicated. Again, this is the difference between energy and power. Power is how fast we spend energy. Okay, work and heat. Work needs displacement or movement. That's when we talk about work. Power produce work or heat. If we have power, we can either produce work, which means move stuff, like moving a turbine blade. Steam has power, we can use this power to push the blade, or we can use heat. And that goes back to enthalpy, which is useful energy. That H symbol has both components to do work or heat. So when you heat steam, you can use that heat to heat a house, or you can use that heat power, steam power to push something, a piston, a pump, a turbine. Okay. Pressure and flow. Think of flow, water in a pipe, current in a wire. heat through substance. They're both the same analogy for flow. Water in a pipe is flowing. Current in a water is flow of electrons. We talked about that in the previous class. And heat through substance. That is our flow over here. It's is this in the video?
Yeah, yeah,
Okay, good.
I put it in.
So heat through substance. And flow buildup is called pressure. If I build more heat, that's more pressure. It could be happening with voltage. You can keep adding voltage, and if there's no displacement for it, or regulation is going to be too high. So there's a big buildup. Same for heat. Flow leads to equilibrium and no pressure. So when we don't have equilibrium, we're going to have pressure. And we said if we raise the water, pump water into a water tower. If you go to New Jersey, the Turnpike, you see a lot of water towers. That's water being pumped. We put energy into it already, so it's full of pressure. So it has a pressure buildup. So it can flow whenever you let it. So flow leads to equilibrium. The entire movement and dynamics of physics, they want to go to equilibrium. Heat want to equalize, pressure want to equalize, electricity want to go to equilibrium. Everything wants to go to equilibrium. So the flow is actually an outlet for heat to equalize inside and outside. If I let this be with no pumping or anything, over time it will eventually be the same. Pressure is the same way. It's gonna go through it. Okay, here's another example. Don't quote me on that. But when you put this helium balloons, over time they deflate. Why? Where do you think the gas is going?
In your body?
Huh?
In your body?
No, it's in a balloon. Where does it go?
I think people suck.
No. If the helium balloon is like it's static, it starts to get radicals, it starts to diffuse over time. What happened? Where is it going through? Over time, it's the membrane.
Yeah.
It's gonna go through slowly, one molecule at a time. It's gonna go. It wants to go to equilibrium. It's under pressure. Same thing with oil underground. It's under a lot of pressure. Once you poke a hole there, back in the days, it will just flow. It's under a lot of pressure. So pressure always wants to go to the easier. I mean, less pressure. It wants to go to equilibrium. Think of blowing into a balloon. The pressure actually, when you blow into a balloon, you're adding pressure into it, and it stays under pressure. Not for a long time. Eventually, it will deflate. So everything goes into equilibrium at some point. Yeah, it's a function of time over ages. Talking about energy again. So we said energy does not vanish. We said the first law is the energy is always going to be there.
And it comes from nothing.
Yep, from nothing. So what's gonna happen? It's transformation. It transforms from one form to another. We're good? Okay, how about transporting energy? Let's say we get the heat in the basement. Okay, that's awesome. How I'm gonna get it to the third floor? There are means to transport energy. I will talk about that, especially heat. So if we want to transport electrical energy, what do?
Current.
Yeah, we use what? Wires. We're gonna make paths for that. If we wanna transform the flow of water, we gotta make channels, right? We try to find a way to transform that energy and flow and make the water go up and down and whatever. We gotta have some kind of path. So we'll have the same thing in heating. We're gonna transform energy from one place to another. Question? Transport. Yeah.
I was just about to say, wouldn't you just need a path if you needed heat to go from the basement up to the top floor?
That's-
Heat goes up.
Yeah, that's a good analogy. You need a path. You need a path, and also you need what? The right pressure. So you can push water over the hill, but it's gonna go up for last examples, heat will go up. They do that. And back in the day, they used to have a stove in the living room, and they have an opening from the living room to the bedrooms, and naturally it will just go by itself. And they used to have fireplaces, and the fireplace has a mantle, and the mantle gets heated up, and the whole chimney will heat up, and they have rods going from the chimney all the way to the floor. So eventually heat will go up and it will heat the house. But again, we gotta think with the function of time for how long it's gonna take. So this would make things faster or slow. So energy will go from one place to another. Example, in a car, transformation. We change the energy in hydrocarbon, gasoline or diesel, into heat, into mechanical, and that's what we want. How will you transform mechanical? Mechanical is happening in the engine, right? Piston going up and down. So we got the mechanical part, which is moving part. We're gonna go to the piston, up and down, shaft, rotating, shaft to the transmission to the axles, axle to the wheel. And every time when you go from one step to another, what happens?
You lose.
You lose something. Losses, 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 losses. At the end, you end up with an engine with a car efficiency that's 35%. What makes the electrical cars more efficient? The motor is right at the wheel. We're done. No crankshaft, no transmission, nothing. Every wheel has its own motor. We're done. So 4 motors, 4 wheels, end of the story. We cut all this mechanical stuff that has weight, need lubrication, it has friction. We cut all that out and we just put a motor at the wheel and we're done. Easy.
Are they as reliable as the gasoline engine?
I didn't look at the reliability, but motors, electrical motors usually are way more reliable than combustion, internal combustion engine, because they have less moving parts, and some motors they don't even have friction in it. They have levitating bearing. So the less friction, less interaction, the more reliable they are. And electrical motors, if they're well built, they last for a long time because nothing can deteriorate them. The only thing that usually goes bad in a motor is the bearing. It's always a bearing problem or overload problem. You shut the motor with a lot of voltage and it burns. Other than that, they can last for a long, long time. Probably you have some equipment from the 70s still running. If it's just motors, it will stay for all time. Okay, so to recap that section, we looked at engine power, engine work, pressure versus flow, energy transformation, energy transport, and types of heat flow. We need to talk about the types of heat flow. How do we move heat from one place to another? How does heat move around the earth, around us, and in a house? Any questions so far? Okay, I suppose